Hi class, how are we doing today? Today we're going to do the lab on looking at evaporation rates, and based on that, compare the strength of the different intermolecular forces within the different liquids. If you remember, an intermolecular force is a force of attraction between two different molecules. There's three different ones that we talked about, so make sure you answer those in the pre-lab ones. And if you have any questions, please feel free to ask, and I'll be happy to look over your pre-lab questions to make sure they're correct. All right, so we're going to do the timing of the evaporation rate. So the idea here is the longer it takes to evaporate, would you think the stronger or the weaker the force is? All right, stronger. So here we go. So I'm going to go ahead and do distilled water, 1 drop, glycerin, 1 drop, and where's ethanol? Ooh, 1 drop. And I know there's pictures of the drops, but you can also get, the video might give you a little bit different angle for your sketches. Don't forget to do the sketches. If you're wondering about the prediction, remember, that's just what maybe you have some background knowledge on this, and so really the only wrong prediction would be no prediction. Okay, so just make sure you fill in that. And so as we wait for the drops to evaporate, and we should have set the timer. Remember, there's a max time of 5 minutes here. Of course, you'll have a timer on the video, I guess. And so I could fill with some intermolecular force jokes, but I really don't know any. Yeah, I'm sorry I've disappointed you. Mr. Hahn, you got anything?
I got nothing.
You hate to force an intermolecular force joke just for some bonding.
I would.
I mean, that would be wrong anyway, because bonding is what type of force?
Well, intramolecular.
Intra with an A. See,
yeah.
that's what made that funny. I know you're laughing. So we could have probably started the other three, but... So just remember to start your timer, because we're not timing it for you. This will be something that you have to do on your own. We will tell you when, via our judgment, the drops are evaporated. Do you remember what how distilled water is different from regular tap water? So distilled water, remember, we've boiled the water and then caught the vapor, and so that's left behind all the impurities. So it's essentially pure water, besides maybe dissolved gases in there. Just kind of looking at the pre-lab questions. In the notes and also in the article from the other day, there was pictures of intermolecular and intramolecular forces. So if you didn't take real good notes, you can go back to the class before and find the picture where that's labeled. I already told my viscosity joke. Perhaps if you're too thick, though, you didn't get it the first time, so maybe I'll tell it one more time. Have you heard?
This is comedy gold.
Have you, well, the definition of viscosity is resistance to flow, right? So the thicker the liquid, and so hopefully you're getting an idea of the different thicknesses. Like Heinz tomato ketchup is pretty thick. So it would have a high viscosity. So if you have a high resistance, you have a high viscosity. And so my famous viscosity joke is as follows. What else is resistance to flow besides viscosity?
Not sure.
Not buying Progressive auto insurance.
Because of flow. Got it.
Of course, it's not as funny the second time. So we are at about 3 minutes right now. It looks like the ethanol is starting to be about evaporated, but the distilled water and the glycerin don't seem to be doing a whole lot.
Yeah, we got still a little liquid ethanol in there.
So would that mean that the molecules in those are strongly attracted to one another or weakly attracted? So that's the thing that you want to be thinking about here. And we got about another minute or so here on the timing.
Looks like ethanol's almost gone. Still a little bit there.
Boy, that glycerin doesn't look like it's changed at all.
Yeah, it's kind of interesting because you can even move it around and it doesn't even, the water and the ethanol move. A little jiggle to it. That glycerin is a solid bead.
This is like it's on the radio. You got to fill the dead time.
Well, or you can just go into an awkward silence for minutes on end.
So I think we're approaching the end of, because I didn't start my timer right away, approaching the end of the first 5 minutes. So we're going to get ready and we're doing this all in one video probably.
Oh, yeah.
Do the next 3. Well, we're going to do all the rest of them, aren't we? So we got unknown number 16 here. Hexane. I think this is the one that you're going to have some fireworks on. Acetone.
And warm ethanol. So again, over 5 minutes and
Okay.
we have water and glycerin still there. Now,
So here is the second batch. I'm resetting I'll start it here. This first one is the warm ethanol. And man, it kind of just dripped right out. I couldn't get a single drop. There's the acetone.
hexane.
And kind of notice how whether it sticks together like the glycerin or it kind of spreads all out.
And we are already losing hexane. You can see the hexane's almost completely evaporated. So at this point,
Kind of move it around a little bit. You can see there's a little bit left. So remember the temperature in the room actually is going to affect the evaporation rate too. At a higher temperature, the liquids will evaporate a little faster. I would say that the hexane is gone, and so is the unknown.
hexane and our unknown
Is it moving anymore?
I'm not seeing any movement on either.
And the acetone is fading fast. I wonder if we put like food coloring, it would make it easier to see.
That'd be a good question. I was thinking about that yesterday. Sometimes they liked it when it was just on the lab bench.
Yeah, the acetone's still there.
Definitely still have acetone, no hexane, no unknown. Our warm ethanol is
Just goof that up.
still there. Acetone is shrinking
Yep,
quickly.
it's about
Watching
gone.
it. The acetone is
It's about acetone. Acetone.
acetone.
I would say the acetone is gone. Call her out.
Yep. And we're still got the warm ethanol up there.
And I kind of, when I was seeing if it was there, I accidentally put a little bit more in there. So that would be an example of some experimental air introduced into. So we're gonna have to make a judgment when the original job would have been completely gone. Everything is gone. If we put it back up here, if we can, you can see that there's nothing left there.
That acetone's still.
That's the ethanol.
Sorry,
I mean.
yeah. Warm ethanol.
Warm ethanol.
Warm ethanol, still hanging in there.
I would say, I think I'm going to call the warm ethanol.
In about 3 minutes or so.
Yeah.
About 3 minutes, 15 seconds or so.
And remember that one, it kind of messed up. And the exact time is not super important because we're comparing the relative rates of evaporation, so that's why I didn't really go back and do that. But we could see that, you know, did it evaporate more quickly than the regular ethanol or not? So those are things that you want to think about, and then relate the evaporation rate, the drop shape, to the strength of the intermolecular forces, and then think about, you know, which force is the weakest? Is it hydrogen bonding? Is it dispersion? Is it dipole-dipole? Okay, and you can kind of, well, the really strong ones are going to be the strongest force. The really weak ones are going to be the weaker force. All right, that's it. I don't know if you have anything else to add, Mr. Hahn, but
Nope. Good
feel
luck.
free to ask